Yeah, so, right, what we're talking about is the Paley Wiener Theorem, right? The connection between, the support of the Fourier transform and the ability to extend your function to an entire function on the whole complex plane with a certain kind of, with a specified growth, right? And what we finished off with last time was that, we finished off with this statement that said that if your Fourier transform, right, decays in a certain way, then then f is the restriction of a function holomorphic on the strip SB, where B is any number between 0 and A. Right. So so this is like a real analytic condition. This is a real analytic condition. You take the Fourier transform, and your Fourier transform decays at a certain rate, right? E to the negative 2 pi I a c, right? But that real condition actually gives you a complex analytic conclusion, right? That your function must be the restriction of a holomorphic function, okay? Which is pretty cool, and it has the nice corollary, well, kind of the immediate corollary, that of course, if if you have that, if your Fourier transform has that sort of decay, and f vanishes on some non-empty open interval, then your function must be zero, must be the zero function, right? We almost don't need to say that, right? That's just an immediate consequence of this, right? But right, so like if your Fourier transform decays in this way, well, then it's a holomorphic function, and if it's zero on some open interval, well, a holomorphic function on some that's zero, that vanishes on an open interval, is zero everywhere, right? That we saw earlier, right? So we almost don't need to state this corollary, but I think it's a cool one because again it's like it's a real analytic condition, right? It's a real analytic condition that relies on properties of holomorphic functions, right? So you've got this condition on the Fourier transform, and if you gave this problem to somebody in just a non-complex analysis class, this would be pretty hard to do. This would be hard to do, right? But because we have this result, we say, oh, look, it's going to be a holomorphic function, and so it's got to be the zero function, right? So that's the cool thing about these results. Okay, so now I said that what we're going to be doing today is the Paley Wiener Theorem. So, any question, Kai? No. Okay. So I'm going to erase this because I'm going to use up a lot of board.
Why
Yes.
specifically 0 times that? Like, isn't it?
Oh, that's an O. That's a big
that's
O.
an O.
Sorry, big
Oh.
O. So sorry, I should have explained that. So if your Fourier transform is big O of this, so being big O of something means that your absolute value is smaller than some constant times that something. So it's just this statement.
Okay.
Okay. So if this holds, then f vanishes on some non-empty open interval. Okay. Is big O of e to the negative 2 pi I, 2 pi a c.
So why does it follow that f vanishes on some non-empty?
Sorry. If this is true and f vanishes on some non-empty open interval, then f must be the zero function, right? Because by the theorem, the function is holomorphic if you vanish on, if your set of zeros has a accumulation point, then you vanish. Then your function is a zero function, as we saw last a couple weeks ago. Okay. So now we're going to do the Paley Wiener Theorem, and this will probably take the entire class actually. So this is a pretty cool theorem that's got a lot of like very sort of like very smart ideas, sort of like smart clever moves built into the theorem. So this is going to take. This is decidedly non-trivial. This is Right. There's some really interesting things are done in this theorem. Okay. So so you start off with a function, so f, which is continuous and of moderate decrease. On R. Okay. And the theorem says that f has a holomorphic extension to all of C. In other words, you can extend it to an entire function. Has an extension to the entire plane with a particular growth. So the size of f must be smaller than a times e to the 2 pi m absolute value of z. Okay, for some m, right? If and only if the Fourier transform, the support of the Fourier transform, is contained in negative m. Okay, so Fourier transform being contained in here means that your function can be extended to an entire function with this kind of growth, and vice versa. Right? If your function being extended with this kind of growth, its Fourier transform must lie inside this interval. Okay. So again, this is no. Okay. Okay. So the proof. Let's do the easy direction first. So so first you say, well, look, if the Fourier transform is supported in negative mm, then certainly the Fourier transform is a moderate decrease. Right, because it becomes zero after it becomes zero outside of here, right? So it's a moderate decrease, and so you know that f and f hat are both a moderate decrease, and so you can use the inversion formula, right? So inversion formula holds. Inversion formula holds, and so that tells you that f of x can be recovered as using the inversion formula. Right, you can recover f from using the inversion formula, but remember this guy is supported on negative mm, so we can truncate our integral to just that finite interval. Okay. Yeah.
What does support mean?
Support means where the function is non-zero.
Okay.
Yeah. So right, you have your function. It lives inside of negative mm, right? So like maybe it does some stuff here, but then outside of there, it's zero. Okay. So when we take the here when we were taking the integral over all of r, well, this thing is going to be zero outside of that interval, right? So we can just say, well, we're only going to integrate over that interval. And so, right, we want to show that if the support is contained, if the support is contained in this interval, then we have a holomorphic extension. Okay. And so what we're going to do is we're going to sort of do the obvious thing, which is define. We'll make the holomorphic extension like this. We'll define f of z as the integral from negative m to m of f hat e to the t pi I z c dz dx. Okay, right? Because that will be an extension, right? When z is real, we get, by the Fourier inversion formula, we get back to x, right? So if x is real, then the right-hand side is f of x by star, right? And so this function extends, is an extension of that function. And by the same reasoning as before, by the same theorem that we invoked the other day, this is going to be a holomorphic function, right? Because this is one of those integral expressions, right? Where, as we said the other day, right? So this is an entire function, right? It is an extension of f, an entire extension of our original f on R. Okay, so that's sort of like that was the easy thing to do, right? We wanted an extension. We had the Fourier inversion formula, and then we just use that Fourier inversion formula to get the extension. Okay. So we still need to show that we have our decay. As for the growth, you say, well, look, if we're looking at, actually, let me, actually, in the book they call, I should call this something else other than f. Let me call it g, right? So, right. So, yeah, right. So g of x is going to be this thing, which is f of x. So, okay. So now let's think about the growth. Well, right. This thing is controlled by the integral from negative m to m of right, of this thing, right, e to the negative 2 pi c times the imaginary part of z. Right, dx. Right. This thing is controlled by, this part is controlled by its absolute value, right? And then this thing, right? This z is x plus iy, right? And the x doesn't, the x part doesn't contribute anything as usual. Only the iy is gonna contribute to the magnitude, right? So we get e to the negative 2 pi y, negative 2 pi y c, right? Everybody okay? Okay, right? Right. And we're trying to show this now, right? So if you think about this exponent, right? The C ranges from negative m to positive m, right? So we can bound the size of this thing by e to the 2 pi m times the magnitude of y, right? Times the magnitude of this thing, right? At the worst, this is the worst thing you can get out of here, right? Because C is between negative m and positive m, right? So this is an upper bound for this term is an upper bound for that term, right? Okay, so we get this negative m to m, f hat C and C. We can pull this term out, and this thing is integrable because of the because it's bounded on negative m to m. It's got the moderate decay that we wanted, right? So we get some constant times e to the 2 pi m my. Okay, which is smaller than what we wanted over here. Yeah.
How do we get that the inversion formula holds? Like what
That was from the that was just a fact basically.
Yeah.
So they said that's a fact from the previous book actually. So that if the function has if the function and its Fourier transform are both have moderate decrease, then the inversion formula will hold.
Okay, and we're assuming that f itself is a moderate decrease.
And then
the support-
going backwards, since the support is finite, it has moderate decrease.
Right.
Yeah.
Gotcha. Thank you.
Yeah. Okay. Anybody have questions? Okay, so that's the backwards direction, and now we go to the forwards direction. Okay. That was the immediate part. Okay, so now we want to go forwards, right? So so we want to show that if f has an entire extension and the Fourier transform grows in a particular way, then the support of the Fourier transform is contained in negative m. We're going to play a few tricks. Okay, so the first trick we're going to play is we're going to invoke a theorem, sort of one theorem of Phragmén-Lindelöf. And I don't know how to pronounce this, but I'm just going to say Phragmén-Lindelöf. Okay, so this is sort of like a maximum modulus principle for unbounded regions. Okay, so I'm going to state this theorem right now, and then after we prove Paley Wiener, we'll get back and prove the theorem. Okay, but I don't want to get sidetracked right now. But here's the statement of the theorem. So that theorem says that if you let S be the interval of, I'm sorry, not the interval, the sector in the complex plane of things that have an argument between negative pi over 4 and positive pi over 4. So S is the sector here. Okay. And if you have a function f that is one holomorphic, on S, 2, continuous on S closure, and 3, the size of F is smaller than 1 on the boundary. Okay. Then you know that the function is smaller than 1 on all of S. So this is like the maximum modulus principle. Remember, we had the statement that if you have a compact set, a compact region, right, and your function is holomorphic on the region, then the maximum must occur on the boundary, right? And so if the boundary, yeah, okay. Actually, I'm lying to you. This is not all everything. So you actually need one more condition. That last condition is that you need f of z to have a certain bounded growth. So okay. So it has to have this sort of bound on its growth. Right? F of z must be controlled by, basically the exponential function. So, so this is the extra ingredient that's needed for the Phragmén-Lindelöf. So with the, with our old maximum modulus principle, we basically needed this sort of condition, but for the unbounded case, we need this further growth condition. Okay, so. Okay, so I'm not gonna prove that right now. I'll get back to it later. Yes.
Is less than 1 for all S there supposed to be for all Z?
For all Z and S. Yeah. Thank you. Yeah. So what it's saying, right, is that if you're holomorphic on S, you're continuous on S bar, and you know that on the boundary your function is smaller than 1 in magnitude, then your function is smaller than 1 in magnitude on the interior.
That makes sense.
Okay. Yeah, it's just like a maximum modulus principle. Yeah. But for a bigger region. Okay, so so that's the theorem we're gonna invoke, and what we're gonna do with it is to use it to actually see that if we assume this bound, then we actually have the bound that we erased over there. Okay, so right, we have this sort of reverse condition, right? Like if you satisfy this, then you actually satisfied a stronger bound. And what we're going to see using Phragmén-Lindelöf is that assuming this is enough to give us that stronger bound. Okay, so we can use Phragmén-Lindelöf to tighten this bound a little bit farther. Okay. Okay. So so step 1, use Phragmén-Lindelöf to strengthen the bound to a e to the 2 pi m times the absolute value of the imaginary part. Okay, so for simplicity, we'll do kind of a simple version, but you can use it to imply the general case. So what we'll show that if f of x is smaller than 1 for all x in R, and we have this growth condition, e to the 2 pi m z for all z and c, then f of z is smaller than e to the 2 pi m y, which you can use to imply the general case. Okay, so here's the trick. So let f of z be the function that we're trying to get control over times e to the 2 pi I m z. Okay, and we're going to apply the Phragmén-Lindelöf theorem to this function. Okay. Oh, I should have remarked. We can also do Phragmén-Lindelöf for like the first quadrant, or you can rotate the argument that we're going to give. You can basically rotate it and do the same thing for like the first quadrant. In fact, you can do it basically over any sector you feel like. Okay, so you can do it over whatever sector you feel like. Okay, I think that will be a homework problem. Yes.
Is this like a 90-degree sector, or can we change
Right.
the angle?
So what we're going to use is the 90-degree, but so this is a 90-degree, and basically we just say you just rotate it. But in fact, the proof can extend to any angle.
Okay.
So yeah. Okay. So what we're going to do is consider. We're going to use Phragmén-Lindelöf on this thing on this quadrant, right? And then we'll do it on all the other quadrants as well. Okay. We won't. We'll just say that you can do it. Okay. Okay. In any case, okay. So think. Well, think. If x is greater than 0, well then, if we look at the absolute value of f of x, right, that's absolute value of f of x e to the 2 pi I n x, right? But we assumed, remember, that that this thing was smaller than 1 on the real axis, right? So this thing is smaller than 1, and then this thing equals 1, right? Because this is just a imaginary e to the imaginary number, right? So we know that we have the bound on the positive real axis. Right. Is everybody okay? Okay. Further, if we take f of iy, well, that's going to be f by y, and we get this e to the negative 2 pi my, right? But we had this bound here, right? We have this bound, which says that this is smaller than e to the 2 pi. Oops, e to the 2 pi m my, right? So here y is a positive number because we're doing it on the positive imaginary axis, right? So we get 1, right? Okay, e to the 2 pi my times e to the negative 2 pi my, which is 1. Okay, so right. So we have the conditions for Phragmén-Lindelöf implied. So what does that give us? That gives us that that this thing, so Phragmén-Lindelöf implies that that this thing is less than or equal to 1, right? But this thing is, of course, absolute value of f times e to the negative 2 pi my. Right? Which gives us the bound that we wanted. right? So this is kind of clever, right? We have this bound, and then Phragmén-Lindelöf allows us to tighten the bound just a tiny bit. Okay, so we actually have a better bound than we thought we did. Yeah.
And to clarify, this is only on the first.
This is only on the first quadrant, so need to do in other quadrants, but I'm not going to do it.
Gotcha.
Yeah, but same thing. Yeah. Okay, so that's the first move. You use Phragmén-Lindelöf to give yourself actually better control than you thought. Okay. Okay. So now. Okay. So. Right. So. Okay, so really what we can say at this point is that we actually have this. This is what we're trying to prove now, right? We've got an easier problem, right? If we have an entire extension and we've got this sort of bound, then our support must be so. At this point, and thanks to Phragmén-Lindelöf, we want to show that if this is true, then our support is within negative MM. Okay, so the strategy here is kind of a interesting and maybe a common one. It's so I was reading Terence Tao's blog, and he calls this strategy finding an epsilon room of space. Okay. In fact, he made a book out of his blog called An Epsilon Room of Space. So this is a pretty important strategy. Okay. So so the idea is basically that you're trying to prove some sort of result, and what you do is you perturb your function, perturb your object of interest slightly. Okay. To obtain an object which for which the result is easier to prove. Okay, so you sort of like slightly alter your object to change it to something that is actually more tractable. Okay. So an object such that the result is easier. Let me say it this way. Obtain an object such that, one, the result is easier to prove, and two, an object that converges to your original object. Okay, converges to your original object as the perturbations shrink. So converges, I should say, like in the right way. So in a way that actually helps you, that actually gives you the result for your original object. Okay, so you perturb your object, you get these other guys, prove it for those other guys, and then take the limit as the perturbations decrease, so you get the result for your original object. Okay, so like finding an epsilon of space. So it's like you're finding some sort of epsilon leeway. Right. Can we mess with the object slightly and make it more tractable? That's really the idea, right? Mess with the object and make it more tractable, right? To give yourself that epsilon of leeway. Okay. Okay. So. Terence Tao, you guys know who Terence Tao is? Well, everybody nods. Okay. So in the world of harmonic analysis, Terence Tao is Stein's student, right? One of Stein's students, actually. Yeah. Yeah. Okay. Okay. So here's what we're going to do. So we'll do it for the case c bigger than m, right? We want to show that the Fourier transform at c vanishes when c is greater than m and when c is less than negative m, right? Right. Our goal is to show that the Fourier transform at c is 0 when c is bigger than m or less than negative m. So we're going to do the uppercase and we'll leave the lowercase as usual. So here's the leeway. Here's the epsilon of room. So for epsilon greater than 0, define f sub epsilon of c as f of c over 1 plus I epsilon c quantity squared. Okay. For the other case, we would take 1 minus I epsilon c quantity squared. And you'll see why. You'll see why in a second. Okay. So the first thing we need to do is to show that let's see that f epsilon does what we want. As epsilon goes to 0. Okay. So here's our first observation that the Fourier transform of f epsilon does indeed converge to the Fourier transform of f. Okay, that's if it didn't do that, there's no point in looking at this, in considering this. Okay, right, and what we're going to show eventually is that these guys are all 0, and that will force this thing to be 0. So, okay, so here's the proof, and here's where I'm going to invoke a theorem that you haven't seen, but it's kind of no way to get around that. So so let's look at the difference of the Fourier transforms. Right. Well, that is going to be right. So remember, right? The Fourier transform is the function times e to the negative 2 pi I, et cetera, right? So when we take the difference here, we're going to take the difference of those two functions, right? We get the difference of those two functions, right? So we would get this guy minus f times that e to the negative 2 pi I blah, right? So what do we get? We get f of x times 1 over 1 plus I epsilon x quantity squared minus 1. And then there's that epsilon term, right? But that has size 1, so we just ignore it, right? That has size 1, so we just ignore it. Oops. Okay, so we get this sort of thing. Okay. Okay, so now x is on the real line. X is on the real line, and so if we look at this thing here, 1 plus I epsilon x, that's 1 plus some imaginary number, right? So if this is 1, then that 1 plus some imaginary number is on this line, right? So this is 1 plus IR, right? Right. So just observe that. Observe that 1 over 1 plus I epsilon x is smaller than 1 in magnitude. Right. All of these denominator guys are on this line, right? So when we invert them, they're all going to be smaller than 1 in magnitude, smaller than or equal to 1 in magnitude. Right. So each of this guy lies inside of the unit disk. When we square it, it'll be inside of the disk of radius 2. Right. Right, the disk of radius 2. So what does that tell you? That tells you that this term is bounded by 3. Okay. So nothing fancy here. Okay. Right. This is the distance. The distance between 1 and something else in the disk of radius 2. Right. So it's controlled by size 3. Okay. So now we invoke the theorem that you don't know. It's called the Lebesgue dominated convergence theorem. Okay. And this is something you'll learn in 137. We take so-called graduate real analysis. I've always hated this name, graduate real analysis, because what does that mean, graduate real analysis? If you take it as an undergraduate, is it still called graduate real analysis? Anyway, I've always hated this name. This at Princeton, this is called real analysis. Okay. Okay. And when I took this class, the professor described, so I'm going to give you the description that was given us. It's that if you have a lemon, and all of your functions live inside that lemon, then it's okay to change the order of limit and integration. Okay, that's basically this. That's basically the Lebesgue dominated convergence theorem. Yeah. And this guy went on to win the Fields Medal later on, so maybe we shouldn't laugh too much at his at his simplification. But yeah, this was Kurt McMullen. I'm not sure where he is now, but yeah, later he got tenure at Princeton, which was almost unheard of. Like Princeton does not give tenure to its professors. You go there and then you leave. But in his case, he went there and then they invited him to stay on as a full professor. So, and then later he won the full Fields Medal. So, he's a clever person. Yeah. Okay. So what's the point here? That this function f of x, right? F of x is a moderate decrease, right? Right. It satisfies this condition. If you graph this condition, you'll notice that it looks like a lemon. Okay. It's basically saying that you lie inside some sort of lemon. Okay. And so, right, so you've got this, and then you've got this 3 that doesn't change anything, right? You just scale the lemon slightly. So what does it tell you? So Lebesgue dominated convergence theorem says that Well then, if we're taking the limit, so the limit as epsilon goes to 0 of this thing here on the right-hand side is the same thing as the integral of the limit as epsilon goes to 0, right? But as epsilon goes to 0, this term vanishes, right? This term vanishes, and so we get 0, right? So that tells us that the limit as epsilon goes to 0 of this thing is 0, right? In other words, that the Fourier transform of the perturbed terms actually does converge to the original Fourier transform. So it does what we want it to do. So, right, so f hat actually does converge to f. Yeah. Okay, everybody all right? Everybody following? Okay, so so that's observation number 1. Observation number 2 is that the perturbed functions actually satisfy a stronger bound. Okay. So we've taken our original function, we've sort of altered it a little bit, right? We've put this factor on it, right? And it turns out that the Fourier it turns out that that those functions will that those functions will actually satisfy stronger bounds. Okay, so let me show you what I mean here. Check something. What am I saying? Sorry, I said something completely wrong at the beginning. In the statement of the theorem. Sorry, what was I really thinking? Yeah. Yeah, so I wrote, I'm really sorry about this, but I wrote that the statement is that f has an entire extension to C such that the Fourier transform, and this is the wrong part, grows like this. Is if and only if the support is contained in negative m. Right. That's not right. It's the function. F has an extension such that the function has this bound, right? Not the Fourier transform, because yeah, that's not what we're trying to show, right? So everything is right. I just misstated it. I misstated this thing at the beginning. Okay, so yeah, there should not have been a hat. No hat there. Okay, so right, so our function right now, our function satisfies these bounds, right? Right. We start off with this function satisfying these bounds. Phragmén-Lindelöf says that we can actually strengthen the bound, right? So we start off with this assumption, right? And then Phragmén-Lindelöf tells us that we can actually change it to this assumption, right? And then we consider these perturbed functions. Okay, and it turns out that the perturbed functions satisfy an even stronger bound. Okay, and because those perturbed functions satisfy the stronger bound, we'll be able to show that their Fourier transforms do vanish outside of the interval. Okay, and then this result will imply that the original function's Fourier transforms will vanish outside of the interval. Okay, is the layout clear? Yes.
But we only needed the Lebesgue dominated convergence to show the exchanging of the integral and the limit. And that last part you said about if the f epsilons all vanish outside of our interval, then f vanishes outside of our interval. That's just convergence. Right?
Well, we needed to show that these guys actually turn into this guy.
Right.
It's by Lebesgue dominated.
Yeah.
So, and what we're going to show is that these guys are all 0.
Right.
And so this guy must be 0 also.
Okay. Are all 0 outside the interval?
Yeah.
Okay.
Yeah.
Okay.
So as long as C is bigger than m or less than negative m, then these guys are all going to be 0,
Right.
and so
So
these guys are also going to be 0 outside that interval.
Gotcha.
And that's what we want, right? We want to show that if we have this kind of growth and we're an entire function, then our Fourier transform vanishes outside of the interval. Okay, sorry about that. That was completely wrong. Okay.
I don't know if it's right in your notes, but in my notes when I was taking it down, when you first wrote it, I wrote it down the way that you just had it. So I think you said it correctly and put it on the board, right?
Okay, good. 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 Glad to hear it. I'm not completely crazy. Okay. Okay. So remember the strategy, right? We've got the epsilon of room, right? We've got the epsilon of room, and we're going to show that we can do it. We can do it for these guys, the modified guys. Okay. So observation number 2. These guys, the f sub b satisfy stronger bounds. Okay. So observe. Yeah, in my notes it's wrong, so I thought maybe I'd written it wrong. So for fixed epsilon, and for y less than 0, and that you'll see why that constraint doesn't bother us later. If we look at, so we're gonna prove the stronger bounds, which are that the stronger bound is going to look like this. That this thing is controlled by a 2 pi m absolute value of y, but we also have something better. That's over 1 plus x squared. Okay, so the perturbed functions are even better than what the assumption that we had on f. Right. This is what we have on f, and the perturbed functions also have this decay. Okay, so right, so right? Here's f sub epsilon of z. We know that the top is, we already know that the top is controlled by this sort of thing. Right? That's what we got from Phragmén-Lindelöf. Right? And so we have this thing on the bottom, 1 plus I epsilon z quantity squared. Right? But you work it out, and it's that denominator turns into very easily 1 minus epsilon y quantity squared plus epsilon x quantity squared. Okay. So, factoring out, say, an epsilon squared, we get 1 over epsilon minus y quantity squared plus x squared. Okay, so I'm just doing arithmetic here. Okay. Now what's the point? For y less than 0, this negative y becomes positive, right? So if we throw out that negative y, the denominator becomes smaller, right? Throw out the negative y, the denominator becomes smaller, so the whole thing becomes bigger. Okay. And then that does it for you, right? You say, well, maybe this is just an exercise. So you can control something of this form, 1 over a squared plus x squared, by some constant over 1 plus x squared. Okay. With an appropriate constant. And so you get that this thing is controlled by some constant, e to the 2 pi m y over 1 plus x squared. We're not going to finish. Are we not going to finish? Maybe we can finish. Okay. Okay. So right. So these guys satisfy the stronger bounds. Okay. So so now, what do we need to show? Now it suffices to show that the Fourier transform of these guys equals 0 for c greater than m. And like I said, the case c less than m can be done in a similar manner. Okay, so here, okay, so let's prove that. F sub epsilon hat c is by definition the integral of f cx e to the negative 2 pi I cx dx. Right, that's just by definition. Okay. At this point, we pull the contour integration trick, and we shift it down by y. Okay, so shift down by y, and we get the integral of f epsilon x minus iy e to the negative 2 pi I c x minus iy dx. Okay. So just the same trick we've played multiple times. Okay. Now, if we now look at the size of that, well, by the bounds that we just proved, right? These guys satisfy these good bounds. Let's make use of those bounds. So we get, this is controlled by a double prime e to the 2 pi m my. So y is a positive number, right? Over 1 plus x squared e to the negative 2 pi c cy dx, right? As before, the x doesn't, contribute anything to the size when we use the triangle inequality. Okay, so that's it, right? We get e to the 2 pi m minus c y times some constant, right? Times some constant. Right? Now c was bigger than m, right? So this is negative, and y this thing is smaller than this constant times this thing for any y. So let y go down. So go down to let y become infinite, right? So this thing this term goes to 0, right? Which tells you that these guys are 0, and we're done. So, pretty cool, right? A lot of cool ideas in this theorem, right? That you start off with an assumption on the bounds for the function, and then use Phragmén-Lindelöf to slightly sharpen those bounds, right? And then you use this epsilon of room trick to shift to a bunch of other functions that satisfy even better bounds. Those better bounds allow you to see that the Fourier transform of the epsilon modified functions, the Fourier transform vanishes outside of outside of the interval, and they were chosen in such a good way that they converge back to the Fourier transform of the original function. So the original function must also be 0 outside of the interval. Okay, that's it. Bye. See you next time. So next time we'll do Phragmén-Lindelöf and go onwards.